Yeah, thanks very much. Yeah, so I'm very happy actually to be here. I mean, this is a very interesting workshop for me because as you've heard already, and I will tell you again, in mathematics, we often use some of these terms like depth in a very naive and unreflected way, but we are never quite sure what we mean. And let me actually write down a list of some terms that appear all over in our mathematical conversations when we somehow try to put certain results or definitions or theories in perspective, right? And I try to make some kind of ordering here. So one thing that is often said, oh, something is trivial. Well, or obvious, easy, straightforward, not hard, not completely straightforward.
Is that the same as hard?
Well, yeah, hard, involved, difficult, very difficult, well, somewhere here, maybe original, ingenious. How do you spell this? And then at the very bottom, maybe deep. Oops. And in some sense, the ultimate thing that you can say is very deep. Oh, profound. We don't know these words in mathematics. I mean, it's so sophisticated vocabulary. Yeah, let me make a couple of comments here. So trivial, for example, this is certainly a phrase that is overused. So I try to actually forbid my students to use this phrase. So there's a trivial solution of an equation or something like this, but they're not trivial statements in mathematics. So of course there are obvious or easy statements. Yeah, easy is also a word that is overused. You know, if you read a paper and it says, oh, it's easy to see, I mean, then I really reach for my gun. Because usually, you know, it's never easy, and very often this is exactly where the mistakes in the paper are, right? I mean, easy to see just means, oh, the authors are too lazy to write out the argument because the argument is a bit messy and they don't really want to do it, and often they overlook certain cases then. Yeah, straightforward, not hard, not completely straightforward. That is an interesting term because, you know, it's similar to, yeah, I forgot this here. Sometimes one says not trivial. Right, and this is kind of interesting. Not trivial is not actually the negation of trivial, quite the contrary, right? Not trivial is already well, to acknowledge, yeah, I mean, one has to do some real work there to establish a non-trivial theorem.
For example, unsolved things. And you didn't learn
yeah, a non-trivial problem, you're right. You would say, oh, this is a non-trivial problem, right. But let me just talk about theorems of facts and these kind of things, right? Non-trivial is going into the hard direction, right? And well, I mean, then of course we have difficult, very difficult. And then, I mean, the ultimate, you know, stamp of approval is if you say something about a theorem that is deep or very deep. So what I want to do now in my talk is I want to provide you with some material for further discussions from my own personal experience. You know, so I want to tell you about some instances where in my own career I stumbled across certain facts where I thought, oh wow, that's a deep theorem. But let me actually start with something, you know, that we already saw yesterday in the discussion. Let me start with something of the opposite type, namely, let me collect a couple of things that I do not consider as deep. And well, essentially everything that we teach to our undergraduates is not deep, right? So, I mean, I would say the whole area of linear algebra, so not deep. I mean, can you tell me any result of linear algebra that, well, is even in the middle range here? I mean, probably the only thing that qualifies, I mean, we have to work a little bit, is that if you have two let's say, finite dimensional vector spaces, that you prove that two bases have the same cardinality. I mean, yeah, there you have to work a little bit. Or another result in this area, that is at least, well, not completely straightforward, is to show that, for example, a symmetric real matrix is diagonalizable. Yeah, but apart from this, I would say, I mean, there's really nothing deep in linear algebra. One has to put this into context, though, because I think this is due to the reason that things have developed, and now we have the right concepts to talk about these things, and this makes it easy, right? You have the right concepts. The theory just somehow develops itself, given this background, given the historical development. You came up with the right concepts to describe this phenomenon of linearity. Here's another area where I think there are no deep theorems, I mean, at least in these kind of basic undergraduate courses, point set topology. I'm not dismissing these areas, right? I mean, quite the contrary. I think this is a very important area for students to learn. And actually, this is probably, if you really want to learn mathematics, I mean, this is really where you want to start. But very often these statements, topology of the following type. I mean, you have certain hypotheses and certain conclusions, and you just write down the hypothesis, and you manipulate a little bit, and the proof falls out more or less immediately. So maybe the only kind of deeper theorem in this whole area is maybe Tukenov's theorem, that if you have a product of compact spaces, the space is also compact. And again, I mean, we are standing on the shoulders of giants here because, for example, this concept of compactness, right? I mean, this is certainly not the first thing that you come up with. Every cover has a finite every open cover has a finite subcover. I mean, why would anybody look at such spaces, right? But, you know, history has shown that this is really the right way to think of certain phenomenon. And well, now we have these concepts, and somehow the theory develops quite smoothly. Well, I don't know. One can also say that if you look at well, one variable real analysis, there's essentially nothing deep there. But again, why is there nothing deep there? Because we have the right type of concepts, right? I mean, continuity with this epsilon delta definition. We have the concept of a limit that took literally hundreds of years to develop. But now we have them, and then the theory, in some sense, runs very smoothly, and we don't have to dig very deep to prove our basic facts in this area. So the only area where I think, you know, from the kind of basic courses that are taught in an undergraduate curriculum, is something like complex analysis, where I would say you have a couple of deep facts that are not at all on the surface has deep facts, I would say, on some kind of elementary level. Yeah, I mean, for example, one surprising thing is that, you know, if you look at functions of a complex variable, and you require that they're differentiable, it implies much more. It actually implies a C-infinity smoothness, right? I mean, this is a pretty deep fact. Nowadays, of course, I mean, we have streamlined the proof to such extent, I mean, that you can, well, give the argument, you know, in a lecture too, but still, I would consider this a very deep fact, even though we have now a very streamlined type of proof. Yeah, let me now move to some areas of mathematics where we have some deep facts, theorems, or definitions. And let me just really tell from my own experience. You know, when I was a student, I was very intrigued by this book by Hofstadter on Gödel, Escher, Bach. And he had a couple of very interesting puzzles there. And let me tell you about one of my favorite puzzles there. So in one of the chapters, he develops what we call a piano arithmetic. He gives it another name. He calls it TNT, the Theoria, I forget. So piano arithmetic. And a quick reminder, so what do you have in piano arithmetic? I mean, you have the usual symbols of propositional calculus. Well, you have quantifiers. Well, okay, you have maybe parentheses. You have variables. You have a countable list of variables, but these variables can only range in the natural numbers. Then you have constants. What else? I mean, then you have these arithmetic operations, but you can only add, you can multiply, well, and you have the equality sign. Okay, and now you can form, statements or predicates. And this whole theory is called, it's a first order theory, it's called Peano arithmetic. So, well, this is something that you can explain to every undergraduate, and now you can start playing interesting games here. Namely, for example, can you say in this formalism that n is an even number? Yeah, so can you somehow express this one variable predicate in this formalism? And indeed, I mean, if you think about this for 1 second, then you would say something like this. So there exists an x, right? I mean, these variables are integers such that 2 times x is equal to our given n. Yeah? So this would express this predicate here in this formalism. And these predicates that you can express in this formalism, they're called arithmetic predicates. So let's push this a little further here. Let's do something more complicated. Well, k divides n. And let me abbreviate this in the following. K divides n. So how do you say this? Well, it's very similar. There exists an x, so that x times k is equal to n. P is a prime number. Well, so for all x we have, so let me use the symbol that I introduced as a kind of abbreviation for this formula. So if x divides p, then it follows that x is equal to 1 or x is equal to p, right? I mean, a prime number only has a 1 or itself as a divisor. You see, I mean, you can start playing interesting games here. And let me mention one of the things that Hofstadter has in his book. So n is a power of 2. Well, we cannot use the 2 to the k symbol, right? Because this is not in our list of symbols here. So how do you say that something is a power of 2? Well, so what's the crucial feature of a power of 2? There are no odd divisors. Or another way to say this, a power 2 is characterized by the fact that any divisor different from 0 is itself divided by 2. So for all x, we have if x divides n, then it follows that x is equal to 1 or 2 divides x. Yeah? So every divisor of n, the divisor has to be equal to 1 or it has to be an even number. Yeah? That characterizes the powers of 2. N is a power of 10. Power of 5. Same thing. You just replace the number 2 here by the number 5. But now comes a difficult problem, namely n is a power of 10. Yeah, and Hofstadter makes the remark, you should not think of this problem unless you know a lot of number theory. And of course, I was challenged by this problem and I thought about nothing else for a week until I had solved the problem. And then I learned a shocking fact, namely a much, much, much more general statement is true. Namely, I was struggling for a week just with a single case, powers of 10s. But then I learned actually from Girdle's paper a theorem that contains this just as one little special case. And I was really absolutely shocked that, well, first of all, you could even speculate that something like this should be true. And then I was also shocked when I saw the proof, namely Girdle proved theorem. Every recursive predicate is arithmetic. Yeah, so I don't have to give the precise definitions, but it's clear, whatever the definition of a recursive predicate will be, I mean, it will allow you to define things like powers of 10. Yeah. So this is actually contained in Gödel's paper, this incompleteness paper that was already mentioned several times. And I would consider this actually as the deepest fact that Gödel proves there, right? I mean, I thought about this as just a special case for a week, and would not have imagined that something of this general type could be true. And what shocked me even more is Gödel's proof. I mean, it's just a couple of lines long, but it's absolutely ingenious. He sets up some extremely clever recursive algorithm, essentially, to be able to give recursive definitions in this formalism of piano arithmetic. So in some sense, I mean, this really blew me away. And in some sense, this was the first exposure to deep mathematics that I ever had. So by the way, on your flight back, I mean, if you want to think about this, is absolutely fun. So let me give another example of something that I stumbled across when I was a student. And this result is usually hailed as one of the landmark achievements of 20th century mathematics. It's a relatively short paper by John Milner, where he constructs what are now known as exotic spheres. So the theorem is this. So John Milner, well, I think 1956, there exists a smooth 7-dimensional manifolds that are homeomorphic to S7, but not diffeomorphic. Actually, for this theorem, Milner then later got the Fields Medal, and just recently, for example, the Abel Prize in 2011 or so. Yeah, I didn't write here when he got the Abel Prize, just recently. So let me explain some of the terms. I mean, I don't want to get too technical here. So this homeomorphism, of course, refers to maps, well, that have continuous inverse maps in both directions, but diffeomorphic here refers really to smooth maps, right? So you essentially have C-infinity smoothness, so you can differentiate up to arbitrarily high order. And this result at the time was a somehow complete shock to the mathematical community, because nobody would have been so bold to speculate that something like this might be true. So I ran across this as a student because I took a basic class on differentiable manifolds that was somehow unsatisfied with the way, for example, you define a smooth structure on spheres, because you choose an atlas of charts and then you work with this. And I always thought, well, I mean, these choices are kind of arbitrary. I mean, why do we pick this particular atlas and not some other atlas? I mean, nowadays, of course, my answer would be, well, if you have a submanifold of Rn, I mean, then it has a canonical smooth structure, so it doesn't really matter which atlas you take. But anyway, so I asked my professor about this, and he gave me the paper by Milner to look at. And I looked at it, and of course I didn't understand a single word, right? I mean, there was an extremely heavy dose of algebraic topology, and I hardly knew what these things are. And at Michigan, I taught myself actually the differentiable manifold class, and I thought, well, maybe it would be a good idea actually to look at this paper again, and maybe as a continuation of my class, present it to students. And I looked at it again about 10 years ago, and I thought, oh well, that is actually not so bad. Yeah. So, and it's a beautiful but very deep idea what Milner does there. So let me just try to convey the main idea here. Well, not so bad in the sense, at the time when I first looked at the paper, there were all these things that I didn't know, but, fortunately I did learn something in the meantime, and then I thought, oh, well, I mean, yeah, that's really manageable even for, first-year graduate students. So how does he get these so-called exotic spheres? Exotic spheres. And his idea is simply this. It has to do with the quaternions, so we'll come to this in a moment. But somehow his starting manifold is just the four-dimensional sphere. And to bring in quaternions, he thinks of the four-dimensional sphere as R4. And R4 really is the quaternions. Plus point at infinity added. And we want to write this in, as a union, essentially, of two well, chart neighborhoods here. So U0 is just R4, and U1 is R, well, let me call this here, as usual, R hat 4, R hat 4 minus 0. And, well, the intersection here is Rn minus 0. Okay. And now what Milner does is he constructs, well, the technical term is he constructs a vector bundle by taking these pieces of the four sphere and crossing it with R4. Again, you think of this R4 as the quaternions. And then you somehow want to glue these things together. And the gluing procedure goes like this. So you have a point, let's say U here, you have a point V. And you want to identify it with the corresponding pair over there. And here the base point U is the same on the other side. And here you also have the V, but now you somehow twist these fibers by multiplying with these quaternions here. So let me leave a little space. So, and the point is this, namely, because quaternionic multiplication is non-commutative, you can multiply from both sides. And you can actually multiply with different powers. So let me stick to my notation here. So H and J. So you can take these powers, well, and if you want to normalize things so that by what you multiply with has absolute value equal to 1, maybe then you want to divide here by the norm of the quaternion raised to the right power. Yeah, so this is actually not so bad. And now, so for each pair of integers h and j, you get a vector bundle. And what you just take is, well, the fancy term is you take the unit sphere bundle. In other words, you just look at these v's that have absolute value 1. And this is why I wanted to write it this way, because this is a condition that is preserved here by my twisting. Sorry, I should have written a U here and a V here. Okay, so, well, let's not get too technical, but let me quickly tell you what Milner now does. So he has to show that some of these manifolds here are homeomorphic to the seventh sphere. And he actually shows that if h plus j is equal to 1, then this manifold is actually is homeomorphic to the seventh sphere. Yeah, this is my notation here, homeomorphic. So the argument is not very hard. Essentially what you do is you look at your manifold and you write down, well, what is called a Morse function with two singularities. And then it's a very general fact that if you have a manifold that admits a Morse function with two singularities, then it has to be homeomorphic to the seventh sphere. So the picture to have in mind is, you have a sphere, and the Morse function on the sphere is something like the height function, right? And you have two singularities here, two critical points, a max and a min. And it's a general fact. I mean, if you have a manifold with a Morse function of this type, it has to be a sphere. That's an easy lemma. But then comes the hard part and the ingenious part in Milner's argument. Namely, he somehow has to show that among these pairs with this condition, there are some pairs where the manifold is actually not diffeomorphic to the seventh sphere. And I mean, he cooks up some extremely clever invariant for your manifold that has to do how the manifold bounds an 8-dimensional manifold. Yeah, and the cartoon picture that you should have in mind is something like this. So you have the 7 sphere here. Then we looked at this vector bundle by, gluing these R4 fibers here. Right, and then we somehow took the unit sphere and these fibers, and our total manifold is somehow the boundary of this tube. So this is our 7-dimensional manifold, and it bounds in a natural way what is called the unit ball bundle, the 8-dimensional manifold. Yeah? So our construction comes with additional data. So the 7 manifolds are somehow the boundaries of 8-dimensional manifolds, and Milner somehow uses this fact to cook up some kind of quantity that can be computed from this in no matter how which manifold actually bounds the manifold. So it depends just on this manifold. And well, if the manifold is the standard smooth sphere, then you can take the unit ball and you can show, well, the invariant then is 0. So if you can somehow compute the invariant in a different way and it's non-zero, well, then he has a smooth manifold that is homeomorphic but not diffeomorphic to the sphere. Yeah, and well, I mean, to make a long story short, so this actually, as he shows, works if you take h equal to 2 and j equal to -1. Yeah. So why do I consider this work as deep? Well, first of all, you have to choose the right type of candidate objects that you want to consider. Okay? And I mean, this is not the first thing that you can up with. So, I mean, one feature is here that you use the quaternions, and this gives you a lot of things to play with because the multiplication is not commutative, and you can write these factors on both sides. So you get a nice range of parameters that you work with. And then I would consider this as more the straightforward part of the argument, and you show that for certain combinations of these parameters, you do get topological 7th sphere. And then the really hard ingenious part is to cook up some kind of quantity that you then can use to show that the object that you get is actually not a smooth 7 manifold. Yeah, so it's an absolutely amazing argument. It's actually not that long, this argument. The paper is relatively short. I think it's only like 10 pages. But I would measure its depth by these ideas that come into the proof, in particular this part here. This is really, it's absolutely amazing how he came up with this idea even. So let me actually move to something that is a little closer to my own area of research. And if I have time, I want to mention 3 examples from roughly a similar area, namely geometric group theory. So in geometric group theory, the basic objects that you want to understand are actually infinite groups, not finite groups, infinite groups. You want to look at them from a geometric perspective. So what you do is this. You take an infinite group. So let me not say this. And you assume that it is finitely generated. And you take some list of generators. And then what you look at is a geometric object called the Cayley graph. Yeah, instead of giving the general definition, let me just look at a quick example here. So you have what is called the free group. So it's generated by 2 elements A and B, right? And then you can construct a graph where actually the vertices are the group elements. And then you connect 2 group elements if one is obtained from the other by applying one of the generators or its inverse from the right. Yeah, so for example, in the free group, I mean, you would get a picture that kind of looks like this. A inverse, well, then you have A squared here, from the right, AB inverse, and so on. Yeah, so the Cayley graph is actually a tree in this case. So Cayley graph of a free group is a tree. So the basic problem in geometric group theory is to somehow recover algebraic properties of your group in question from geometric properties of the Cayley graph. And well, let me give you an example of a typical type of question that you can ask in this context. Namely, with this Cayley graph, there's something related. It's called the growth order of the group. Yeah, so it's a function on the integers. The definition is very simple. Namely, you just look at your Cayley graph. You think of all edges of having length 1. You just look at the cardinality of the ball of radius n that's centered at the unit element. Let's say the closed ball to be specific. Okay. So somehow this a growth function is an important characteristic of the group. So for example, if you have a free group like this, what can you say about this growth function? Well, each step you go, you get 3 times as many vertices. So if you go out, you get some kind of exponential increase. Yeah, so free groups have exponentially increasing growth functions. Well, if you take a group like Zn, for example, yeah, with some natural set of generators, as you can imagine, then you get polynomial growth. Well, this already motivates the first question here. It's actually a problem also due to Milner. I forget when he raised it, maybe also in the 50s, 60s. So we have exponential growth, we have polynomial growth. Is there anything in between? So are there groups of intermediate growth? Yeah, so this is the name for it. So groups where the growth rate is neither exponential, not quite as fast as exponential, but super polynomial. Yeah, and this was an open problem for decades. And then came Geroch, a Russian mathematician, and gave an example of a group of intermediate growth. So Geroch gave example of group of intermediate growth. And this example is absolutely amazing, and I would consider this a very deep a contribution to mathematics. And the example is actually not hard to explain. Maybe I don't want to do it. So it has to do with automorphism groups on a binary tree. And it's generated by 4 elements. So it's in some sense a very, very simple object. But I would never have imagined that this could be an example of a group of intermediate growth. So so I wonder where he got this insight to even look at this kind of object. So I would consider this a sign of depth here that it's a very original construction. It's also very surprising. I have not the slightest idea how he came up with this example. So another instance in this area of depth is not an example, but rather a theorem that has to do with these things here. Namely, it was a conjecture again for decades. Namely, if you have a group of polynomial growth, then it should look in many respects like Zn. Well, I mean, there's some slightly more general examples. For example, if you look at a matrix group of this type here, yeah, it's a so-called Heisenberg group. So x, y, and z are integers. So you can show that this is a group, and it actually also has polynomial growth. And the conjecture for decades was that essentially every group of polynomial growth has to look in a certain way like this. And the technical term is it should be a so-called nilpotent group. So the conjecture was every group of a polynomial growth is, yeah, the term is virtually nilpotent. I mentioned this term already yesterday as the most basic and elementary fact about polynomials here. And it turns out that this is a theorem now proved by Gromov in the 1980s. And the proof is steep and ingenious. And the reason for this is that he brings some really very original new techniques into the proof that have, well, I think the right word is transformed the whole area. Yeah, by now it's a kind of standard construction that he uses. The technical word is, he used for the first time this technique of asymptotic counts. I mean, what this is precisely is not so important. I mean, to give you a rough idea, so if you look at Zn from very, very far away, what do you see? You see something that in some sense looks closer and closer to Rn. And this is what he does. He looks at this Cayley graph from very, very far away, and he shows that in a suitable sense, this has a limit. And then he shows by invoking some facts by Montgomery and Zippin that this object is a Lie group, and after a lot of extra work, he arrives up at this conclusion that he wants to establish. Yeah. So, yeah, I think this one aspect of depth is exactly this kind of transformative nature of things. So these ideas that appeared for the first time in this paper have completely revolutionized the area. Yeah, let me actually finish my talk with one example, actually also due to Gromov, which is of a slightly different character. It's not a theorem, a deep theorem, or deep example, but it's actually of a different nature. It's a deep definition in some sense. So deep definition. And again, I mean, this definition has transformed the whole landscape. So Gromov developed by one very simple axiom a theory of spaces that are in some sense negatively curved in the large. Yeah, and if you see the definition, I mean, you have no idea what this has to do with negative curvature, but it somehow turns out this is exactly the right definition that makes the theory work. And the amazing thing is that this definition is very simple. I can write it down in one line. So I need one other term that I have to define first. So you have a space with a metric. And you define a quantity which is now called the Gromov product. So you have 2 points in your space with a base point. So x, y, p are points in the space. And the definition is very simple. It's 1/2. Well, you take the distance of the points to the base point. You add it, and you subtract the difference. So this is the so-called Gromov product. Yeah, so definition, a space, metric space, is delta hyperbolic. Yeah, where delta actually now is well, any non-negative number. Often we call these spaces now Gromov hyperbolic if they're delta hyperbolic for some delta. Well, if a very harmless looking inequality is true, so if there exists a base point such that this Gromov product x dot y with the base point is greater or equal the minimum of x dot z, z dot y, and you subtract a delta. This should be true for all x, y, z in your space. Yeah, so this looks like a very mysterious definition, but I can tell you it turns out that this is somehow a simple definition that captures this whole phenomenon of negative curvature in the right way. Yeah, and this has led, as I said, to a transformation of the whole field. So this was introduced in a paper in 1987. And it has essentially led to a whole field of these so-called Gromov hyperbolic spaces that is closely related to geometric group theory. And I think it's a sign of depth if you can distill somehow the essentials of a whole theory in a simple definition of this type here. Of course, I mean, I cannot convince you that this leads anywhere. I mean, you will not see it from the definition, so you have to take my word on it. This simple axiom leads to a surprisingly rich theory. Yeah. So I think I want to stop here. So I hope that I've shown you some examples, that can contribute to the discussion here.
Coming back to Milner again, was he actually looking for exotic spheres, or was he looking for something else and stumbled on them?
That's actually a very good question. I don't know. I have no idea what the precise history of the result is. Yeah.
I'm just thinking, since they were so unexpected, maybe he didn't expect them either.
I think he didn't expect it either. I think he rather thought, this has to do with the Poincare conjecture. He disproved the Poincare conjecture or something. I think it was more a coincidence that he realized, that this is an exotic sphere.
Yeah. Am I understanding right, the Milner example, that it's that among the striking features is precisely that it is kind of singular. It's a one-off thing. It doesn't lead anywhere. It's not very. It's not.
Well, you cannot say it doesn't lead anywhere. There's a certain industry of exotic manifolds and these kind of things, but it's certainly. I don't know. It was certainly not transformative in the way as, for example, these results by Gromov were.
But the exotic manifolds are all. But what I mean is, it's not as if you generalize this and then you get a whole bunch of other manifolds that are similar. If I understand you right, it's sort of you keep coming up with sort of odd examples that.
Well, I mean, for example, one question now you can study. I mean, all right. So the smooth structure on the seventh sphere is somehow not unique. How many smooth structures are there? And later was shown there are 28 or something like this, right?
Well, I mean, that's true, but you could argue that what this theorem does is tell you that continuous manifolds are very, very different from smooth ones.
Sure. Absolutely,
yeah.
Yes.
I mean, it remains the case, doesn't it? That at this point the roads diverge.
Yeah, I mean, it's right. I mean, in some sense it was transformative because it somehow increased our understanding how we should think of these objects, right? And this made clear, there's a kind of continuous world and there's a smooth world, and since then the paths diverged.
Right, because there is the really striking thing about the last example of Gromov's definition is just that fact that it captures such a wide variety of things,
right?
And sort of in a kind of simple.
I mean, it's hard for me to make this clear in my talk, but So he wrote a 200-page paper based on this definition alone, and it, as I said, it led to the development of a whole theory because this harmless axiom somehow is at the heart of what is a negatively curved space.
So then actually something like, you had mentioned the Tukenov theorem, which I think is an example of this, although on a much lower scale. because as you're saying, you know, the ideas that it used in terms of compact spaces and so on are maybe not the first things that would occur to you. But actually, the original Tukenov form involved what a different definition of compactness, which we call sequential compactness. That is, say every infinite series has a convergent subseries, or a sequence. Yeah, every infinite sequence has a convergent subsequence. And I remember when I first encountered that, wow, that actually is quite surprising, right? I'm not at all surprised by the Tukenov theorem in the way I learned it, but when I see it in that form, I'm really kind of taken aback. That doesn't seem to me the sort of thing I'd expect. And also that the thing about the general form of the Tukenov theorem is that it shows up in a lot of other different places in very different forms that turn out to be, well, you prove you prove completeness for the first order logic. You can it turns out to be equivalent to form of the axiom of choice.
It's a fundamental and maybe even deep result, but we got so used to it that I don't know what else.
Yeah, well, that's what I was thinking is that sometimes it can be that the very process of distilling something to its essence, so to speak, can make it seem, not as profound as less deep. I mean, that's an illusion. I would think. I would claim, but still, it is a psychologically real fact that you get.
No, I think that's absolutely right what you're saying. That if you twist and turn things often enough, and you have the right way of looking at them, then maybe they become not as deep as they seemed at first.
Well, that's something I was going to ask. One of the words we haven't yet said is that that sense that mathematicians tell themselves a story about how the subject goes. Right, and you have these definitions, and you have these problems over here, and these things ought to happen, and these things which we know and have established and are somehow natural and right. And then there are the unexpected things, and those are rather likely to be the ones that we call deep, right? That we wouldn't either we would have guessed wrong, right, or they would have guessed wrong, or at least something unpredictable.
Yeah, no, I would agree. That.
I was thinking, of course, about Andy's talk as you gave yours, and sort of with an extra board over here for what Andy had said, and that's another way of looking at the surprise of this, right? It's not just the statement itself.
Yeah, I would also say that depth often comes with this element of surprise.
Take account of, oops, this bit.
Yeah, no, I would agree that very often, I would say that certain aspect of depth is certainly this element of surprise. This example that I mentioned with Gödel's theorem. This came a big surprise to me. I would not have guessed that something like this could be true. I think this refers. Oh, sorry. This refers back to what we discussed yesterday. These hidden qualities of depth, right? Not on the surface.
Yesterday in conversation, I said that a counterexample to Fermat's last theorem would not be deep, and that somehow seemed like a sort of an obvious statement. But then maybe there are circumstances under which it would have been, where if it led to, if the way one found that counterexample. This example by Geroch.
It's not a counterexample to anything, but it's
a counterexample to the statement that they're all.
That they're all polynomial growth exponential
It's an
growth.
obvious conjecture.
It's an obvious conjecture, exactly.
Now, it would be surprising to have a counterexample to Fermat's last theorem, but that doesn't make it deep. So being surprising doesn't make something deep. So being able, if it had simply been, when it's simply done a computer computation to get a counterexample, that's not. I think I'm reading that.
But why would it?
But it would be
It's a context in which it's surprising, right? Supposing you go back to the situation where you've got, I can't remember, protocol or a certain class or a case of Fermat's last theorem. And I think I remember the first kind and the second kind, so we have a bunch of these things, but no reason to believe necessarily a freaking exponent that's not covered.
Except that you've computed
no ideas at all, right? And then you do your work and you come up with a counterexample, and we all let you down, Alice. We were all a little bit unimpressed.
Yeah.
Right? Because we had no views either way about that exponent, right? So we're not terribly surprised. That's different from saying, hey, we've got this machine, it's heading in this direction.
But we would have been surprised.
It would have been a surprise, but compare the situation where we thought that maybe even you were about to do it, you know, you're known for your work and all of this, and suddenly, damn, you come up with a counterexample, all the methods we had, all the ideas of heading in that direction, and when n's 1001, it just goes wrong. Then we're surprised, and then we're cavaless surprised, it seems to me. Because we had an expectation, we had a belief, and in Milner's case, you had a belief that this just shouldn't happen.
I feel with Alice that a counterexample to Fermat would be trivial because you just have to add and multiply to confirm it. But a non-smooth structure on the seventh sphere, you can't confirm that by anything simple. Milner had to invent this invariance.
But what if he had just done some horrible brute force construction or something really ugly with no intuition that didn't lead to anything else? Then we'd say that's like a counterexample of Fermat's last theorem.
Yeah, it's also the elegance of what he did, you know.
My subjective says you're wrong. For what it's worth.
Now, maybe for Fermat's last theorem, what would have upset people even more was because it was the fact that the Taniyama-Shimura conjecture implied Fermat's last theorem. All of a sudden, it became important to mathematicians. So a counterexample to Fermat's last theorem wouldn't upset number theorists, but a counterexample, but that would lead to a counterexample to the Taniyama-Shimura conjecture, which would be very upsetting. You know, that would totally shatter the foundations of what we expected in number theory.
Just a comment. Maybe this is already everybody else already thinking in this way, and just stating the obvious. But maybe it might be worth just saying for the sake of saying. Maybe we want to distinguish between two ways that we can use the word surprising. Right. One is a kind of psychological fact of whether or not we're surprised by it, and then there's something more, still a little bit psychological, but maybe more objective about whether or not we ought to be surprised by it.
Yeah, this is, I think,
Yeah.
a good example. This example of a group of intermediate growth. You know,
Mhm.
certainly there's this element of psychological surprise. You know, because
Yeah.
some people probably conjectured, you know, there are no such things. But then it's a more objective. I mean, it's a
Yeah.
concrete construction that you have. You know, and it's.
Because I sort of think that I had this just a couple of weeks ago, or a few weeks ago now. You know, I had this experience with my students in logic of presenting completeness theorem for first order logic, and you know, they were all kind of tired and looking a little bit dazed and so forth. And I'm trying to say, look, you should be surprised by this. Right? This is really surprising. And I was, well, whatever. And it's sort of you have to. There's a way in which this is the fact that it's surprising is this sort of I'm not sure what I mean by objective here, but it's a property of it. It's a fact about it. If you set up the issues in the following way and you understand them in the way we normally do, this should really catch you off guard if you understand it well enough. And if you don't find yourself surprised by it, it's a sign that you're missing something. So it's not, we might not want to be too caught up with thinking that being surprised by something is automatically a sign that it is surprising, and that not being surprised by something is automatically a sign it isn't surprising, if you see what I mean. We want to keep those separate.
Is that distinction, or is the right side of that distinction bound up with the idea that we heard a few minutes ago about the direction in which the field is headed, or non-deductive reasons for thinking that something is going to turn out in a certain way? That last we didn't hear a few minutes ago, but I was trying to give one way of cashing out the direction in which the field is headed.
Well, I mean, there might be interactions, but I can think of cases where I would say, as a psychological fact, I find every time I try to read Jacobi's paper on elliptic functions, I'm surprised by every next line. Right, it's just there's these complex substitutions. I'm astonished at what's going on. That's a psychological fact about me, but I don't think it says anything deep about the specific lines themselves, although it might be something about the subject matter.
I meant the objective.
The objective side.
I mean, if the surprisingness arose from the non-deductive evidence that there was available, that things would turn out differently from that. And then we find the surprising discovery. That would give you a non-purely subjective
Yeah.
notion of surprise, in that there was a reason to find this surprising, the reason being these other considerations
Yes.
that were pushing the field in a certain direction. In the case of the historical example, you presumably already knew how the story came out, and so the surprise would have to be, as it were, retrospective, considering how the field had been headed at the time, that you could read in, this should have struck people as surprising.
Yeah, for some reason I have a vague misgiving that there's something else about what I'm trying to characterize that would still isn't captured by that, but certainly that's, that fits with what I'm saying. So that might be part of it.
Well,
Trying to think of an example.
I kind of want to go back to Alice's point in a way, because some of the things that come up. Suppose you came up with Campbell, it was before Funny Answer and stuff like that. So, and it opened up the field, and then there were certain exponents which were the tip of an interesting iceberg. That would be interesting. Whereas if it's just down, we've got this example.
Yeah, so it does depend on how one came about,
Right.
how one found the example, and whether it's
And so I think
classic
it-
examples or,
yeah,
But
I think-
I hadn't realized that till hearing your talk. that
There's some-
There might be some.
There's some sense in which some things kind of, I'm channeling Frank away here obviously, but there's something sense in which some of these things organise a field, right? Either by shocking you, we didn't expect Milner's result, but we've got to deal with it, or by answering your dream. We would have loved a theorem like this, and lo and behold, there is one. But either way, this is a departure from the story you quietly tell yourself, right? The Marc's phrase, which I've already forgotten, is rather nice, the non-deductive. That's it. The non-deductive side of the organisation, right? So the deep bits would be the bits that somehow, whether you like them or have to learn to love them, don't come very easily out of that non-deductive part of it. So what you were saying yesterday, let's try to take the contingency out by saying, given these facts, then it is rational to do this, right? Well, given these facts, it is somehow surprising, wonderful, or distressing that this turns out is a measure of its depth.
Although I realize now maybe what it was that still was nagging at the back of my mind in when we're talking about direction of research. In part because the facts in question could be exceptionally basic and rudimentary, having nothing to do with research as such. And I'm thinking of quadratic reciprocity being one, where you really don't have to know very much about any arithmetic research to understand the statement of it and find it absolutely astonishing. And it's true that the more you learn about it, the more astonishing you might find it. And so that's sort of a case of something where I would say that's sort of objectively astonishing. It's something where even learning why it works, even really laying out what's going on, doesn't seem to take away the surprise at all. Even sort of reaching the point where you could quote it in your sleep, where it's somehow there's some way in which it cuts against the grain of the type of you get used to a certain kind of pattern, you get used to a certain kind of order, even when you're just dealing with elementary arithmetic, and then this crops up and it just seems thematically out of place.
Yeah.
It's I award it to a mathematician when she has either discovered this fact or come up with a new proof of it or whatever, and it's just a term I use for highest praise. And if that's the case, it would seem like to try to distinguish it, is it the same or is it different from surprising, or is it the same or is it different from original or explanatory or fruitful, that seems like a wrong-headed. It just means best mathematician, Luberman Prize. I wonder if that's your sense about what that.
Yeah, I think, when I say very deep, I mean it as a praise of somebody's work. That's certainly one sense of, but it has many shades of meaning, I would say. So you can also, I don't know, we also use it objectively when we just talk about certain proofs. Oh, this is a very deep proof, and this is no reference to any person who actually proved that. I think this word deep has many different meanings, and that's maybe something that we try to clarify here.
Let me take another shot at asking what I think is a similar question in the same spirit. If very deep is this somewhat amorphous, great honorific, then I guess I would expect that you couldn't say, well, that's not very deep, but it's got this other tremendous mathematical virtue in great quantity, because very deep seems to reflect sort of all the virtues rolled up into one. It seems like a proof could be very elegant without
without being very deep. Yeah.
Theorem being very deep.
Yeah.
Or beautiful.
Yeah.
Or I'm trying to think of other.
No, you can have a
terms.
Yeah, beautiful theorem, but not very deep. Sure.
I mean, is this in the same ballpark?
Yeah.
So that would then the possibility of that would count against very deep being nearly the.
Yeah, this linear order, I don't know. I mean, this should not be taken too literal here, the linear order.
Simplicity is also a virtue, but it can't at the same time be simple and deep.
Yeah.
It can.
Oh, maybe, but not generally. Not all.
No, I wouldn't, yeah.
Just wanted to return to an earlier discussion. I think mathematicians show a shocking prejudice against counterexamples, and you can see that in the Clay Mathematics prizes. If you look at the website of the Clay Mathematics Institute, you'll see that if you prove the Riemann hypothesis, you get $1 million. End of story. Okay? If you produce a counterexample, well, they'll think about it. Really, I'm serious. Here's what they say. If in the opinion of the Scientific Advisory Board, the counterexample effectively resolves the problem, then the Scientific Advisory Board may recommend the award of the prize. If the counterexample shows that the original problem survives after reformulation, okay, so that's a different problem, okay, or elimination of the special case, then the Scientific Advisory Board may recommend that a small prize be awarded. Now, isn't this rubbish? I mean, look, if I produced a counterexample to the Riemann hypothesis, which would be extremely difficult because it's been checked up to huge numbers, right? I mean, it would be a major accomplishment, right? I mean, look, I've refuted the Riemann hypothesis, right? I mean, it's refuted.
That's all it means.
Sorry?
It could just mean you had an expensive computer. Like
No. It's completely
Sure.
out of
Like
computer
for
reach.
miles
Forget
less
it.
than-
Computers are useless in this area. Turing was wrong. Turing thought he could find a counterexample. He was just completely up the creek there. Really. No, I mean, look, but look, logically speaking, if I produce a counterexample to the Riemann hypothesis, I've refuted the Riemann hypothesis, right? End of story. Right? Why don't I get $1 million? It's sheer prejudice. Prejudice.
Okay. No, it isn't, I think.
Hey, I want my $1 million.
No, I'm going to stop you getting it. No, I think it's for we go back to Arthur's point. If you come up with this counterexample as a result of some complicated deep arguments that we had misunderstood the Riemann hypothesis in some way, I'm sure you're going to get a large amount of money.
Oh, good.
I hope so. Halfway there.
A simpler case might be.
But not if you just get lucky. I mean, and in this particular case, probably the computer search won't do it. But
Right.
you have to have some I come back to the story. You have to have some contribution to the story that makes us go, oh wow, that's good. Otherwise, and especially with the advent of computers, we just go, okay, fine. Gee,
architecture, would we admire that as much? No, I don't think so.
Makes me think of Lakatos, is that how you say it, his book?
Yeah.
About Euler's, the development of Euler's formula and the proof, where the process of proving it was as much about trying to establish the correct statement of the theorem as actually verifying it, which some already thought was true ahead of time. So often if we find our kind example, that may just be the next piece in the story to find the correct statement.
True enough.
So, on the other hand, something I learned from Barry Mazur is, to some extent these things are psychological. So you may be trying to prove a theorem and then you discover that this theorem is false, and you have choices there. You can decide you're going to go into a deep depression and give up mathematics because your dream of proving this theorem isn't going to happen. But, I mean, so with Barry Mazur, if you happen to have Barry Mazur around, he's going to love him and say, oh, but that only makes it more interesting. And then you go and you realize, and that's what happened with Milner and Alasdair's theorem. I mean, basically he made a mistake and assumed that all number fields have class number 1, and it turns out they don't. But that only makes it more interesting. That's why we have this richness in algebraic number theory. So, and that's why we have this whole field that was built with this original goal of proving Alasdair's theorem, which now number theorists think isn't really all that interesting, but all the techniques are and allow us to do all sorts of other wonderful things.